So yeah, before we begin, like how many of you here like know what roll-ups are in general and why do they make sense? Oh, yeah, quite a few. And any idea what micro-rollups could be like besides the name micro and like them being smaller and like more efficient? Okay, cool. Yeah. So ideally, what happens with roll-ups are is that the purpose of a roll-up is to take out the computation load and replace it with the storage load on an L1 chain. So current gen L1s, and I like dividing the layer ones into three categories, which is Gen 1 layer ones, which is Bitcoin. Then there is Gen 2, which is execution environment on top of a shared consensus. And then finally Gen 3, which is the modular blockchains, wherein you can just plug and play whatever part of the stack that you want to change. So ideally, what we are doing is building on this third layer, wherein we have separated the execution from it, and rollups are that exactly. So let's say this is like one layer, and this is the other base layer. And what essentially happens is instead of it forming blocks over here, and then that gets expensive because as more people interact with L1s, then there is a gas market which prioritize people with higher gas fees and all of those things. And this was pre EIP 1559. So the gas prices and all of those things were like shooting crazily high, and it was becoming very difficult and almost impossible to interact with the parent base chain. So what we did as like in the roadmap as well, what happened next was there was something called as plasma, and then based on plasma, then there was side chains, and then finally the community decided to settle on something called as rollups. So what rollups essentially do is that instead of transacting on the parent chain, you transact on a chain which is a layer above that, and then whatever happens over here in some form of computation proof, you submit that on L1, and what essentially happens is that this block now contains all the data that is required to reconstruct any kind of compute that happened on the rollup. So this is a rollup, and this is the parent chain, and whatever computation that happens on a rollup is then rolled down. Actually, like I would say, like roll down is a better term, but yeah, rollup basically takes all the data up a layer and then rolls down the transaction proofs and all of those things on the parent chain. So that is like a basic overview of what rollups are and should be. But in general, what happened during like 2017, 2018, like during that time when people were starting to develop rollups, that they wanted to give an exact same experience of building applications as they do on layer one. So that ended up replicating the same problems on a rollup as they were on L1. So you had an EVM state machine. That EVM was again replicated on a rollup, and then you ended up having an EVM running on top of an EVM. So I don't think that is very efficient because you are actually inheriting all the problems with the parent chain, just trying to put a band-aid on it and then like just working things out. Then came up something called as app-specific rollups. And the purpose of app-specific rollups was to remove the general purposeness of the rollup chain and replace it with some specific features. And that ended up like that was a successful attempt at it, but then that ended up having like so many different chains. So everyone is aware of how there are so many L2 chains, and there was a recent meme called like in the current time in the recent future there will be more chains than there would be applications. So what's the solution? The solution here, and that is something which we feel also the purpose of rollups were to have app specificity by default. So instead of just replicating the state machines on L1, you do something else on a rollup, and then that kind of settles down on the parent chain. So instead of building a general purpose VM, what if you could build an app specific VM that only works on your application, and then that is very efficient and very cheap to run. And that is what we did with Micro-Rollups. So essentially, yeah, I just explain it in the same diagram. What we did was we removed the general purposeness of it and replaced it with a state transition function in which your application logic is enshrined. So Micro-Rollups are still blockchains, but the blockchain's state transition function or the block production logic is actually your application's logic. So instead of you transacting with a micro rollup and then sending like a EVM transaction on top of it, what you do is essentially, let's say let's think about a use case. Let's say you want to build a payments application, and the purpose of your application is just to do payments and not care about NFTs. Like we, in most situations, most of these use cases are isolated enough that it is efficient. It is enough to just focus on that use case and have like something else on a separate context. So how about you change your block production logic in a way such that every block transaction is just a payment to from one address to another address, and that is all. So essentially, a transaction, instead of it being an object wherein you have the to address, the from address, then you have a value which is the each, and this is like a regular each transaction. You have to from value, and then you have call data and nonce, then base fee, and I think there are around 15 different parameters on it. What essentially you need for a payment transfer is the sender, the receiver, and the amount, right? So why do you care about all the other things? So how about we build a state machine that can only take the transaction which is the from address, the to address, and the amount. And this is it. And also, since it's running in your context, right now the Ethereum addresses are 20 bytes, and that is because of a limitation that's how the storage is structured. So if you are running it in your context, and let's say you want to work only with, I don't know, let's say 1 million users, so you can easily do million addresses in, I don't know how many bytes, 30 bytes, I think. So the transaction could just be like 30 bytes for 30 bits for from 30 bits for to, and amount could be like, let's say, 256 bits, and this adds up to like, I don't know, 316 bits, which is, I don't know, less than how many bytes. It's divided by 8, so I don't know, 20 bytes or something. No, 30 bytes. Yeah, it's like around 30 bytes, and your entire transaction can be done in 30 bytes. Instead of you spending so many bytes of data on just doing something on Ethereum, you can just spend 30 bytes and just be done with it. And that is how we came up with the concept of micro-rollups, that your VM is essentially not a general purpose VM, but something that you can modify such that the state transition function only works on the data which is relevant to you, produces blocks, and then store enough proof on chain such that this 30 bytes is verifiable. So if I am sending someone some tokens from my address to someone else's address, and I can do it in 30 bytes, and that is verifiable on chain, that's enough to do a blockchain. So that is like the basic concept of what micro-rollups are. And happy to take any questions in between before I move on to the next part.
Is the benefit that the cost is less, or is the benefit that the latency is less?
Both. So instead of you processing, so for EVM, the latency comes from consensus. For all the general purpose use cases, you need to have, you have a global state, and that global state is accessed by NFT projects, DeFi projects, gaming projects, all of the projects, and you have to process all of them and then produce a block that encompasses the global state and moves it to the next state. And that has certain amount of work required to be able to prove that, and the consensus algorithm takes like 12 minutes to do it, right? For the finalization. Over here, you just care about the transactions. So instead of you doing a 12-minute consensus, you can just say that, okay, if my nodes are light, since the data is less, you can perform the same amount of compute in less number of times. So you can have like a faster consensus there.
Would you compare that to an L2 and say that's still the case?
Yeah, this is an L2.
Stackr is an L2? No.
Yeah, Stackr is a framework for building L2. So Micro-Rollup is a L2 SDK, and Micro-Rollups are just that the framework is different than a general purpose L2. It's just that the L2s still settle on L1, and that is the part of my next section, and that's how it is. So the data is less, so the cost is less, and the data is minimal, so the time or the delay is minimal as well. Yeah. Anything else from anyone? Yeah.
Are you using Wasm runtime here?
Yes. So yeah, also that's like the next section as well. So we have the SDK right now in JavaScript. We have a compiler which takes all your state transition logics and compiles it to Wasm. And then the Wasm is something which goes to execute on our validator layer, and then that goes on L1. So Wasm is the base. Nice. Wasm is the base WASM is the intermediate execution environment, and we can write the SDK in any languages. So right now we started with right now our SDK starts with JavaScript because we want to target the web devs. Eventually we'll have an SDK in Python to target the AI developers, and then from there we'll also look into Rust and Go. Alright. I'll quickly move on to the next section, which is how the architecture of Stackr looks like. Seems like a very big elevator. I don't know, is this Doordarshan music? Nice, right? Cool. So yeah, so the next section is about how the Stackr SDK is architected. And this actually also talks about how it is an L2. So let's say this is Ethereum. Okay, let's not say it's Ethereum. And the entire L2 stack is a lot inspired by Polkadot. Inside our L2 stack, we have two layers. One layer is called Vulkan, which is used for verification. And then on top of that, we have the application layer. And inside the app layer are micro-rollups. So what essentially happens is these micro-rollups are running in a centralized environment, and I'll talk about how decentralization comes into picture after that. And because these are centralized, they run exactly like any regular backend application. So we have constructed it in a way that any Web2 developer can get started with it immediately. They can just import the SDK, put it inside their Node.js application, and it will start producing blocks. So a user would send transaction to the MRU. The MRU will immediately return a response because it runs like a backend application, and this is around like a few milliseconds in latency. So we tested our MRUs to produce blocks, block time, like the lowest block time that we tested was 1 millisecond, and that could still include like around 1,000 transactions or so if you construct it nicely. So this part of the cycle is complete, and that is where you get the efficiency gains from. Now the question would be, how do you get the security gains from? Like, if this is a regular backend application, you could do anything. It's a centralized environment. The database is centralized. Anything can happen. So the answer to that is that once the response is given out to the user, the MRU produces blocks, and this block goes to the verification layer, over where on top of which we have a committee of Vulkan operators, and these Vulkan operators take in a block, verify it, produces a proof for that block, and if the consensus agrees to it, it will settle it on L1. It will actually split data into two parts and settle it. The block roots are settled on Ethereum, and the block data, or like the transactions, are settled on DL. So this is where the decentralization part comes from and the security comes from. So it essentially runs as a network in its own, which can communicate with the user in Web2 application like speeds, and then still provide decentralization benefits to the user because of this mechanism. So yeah, that's like the entirety of Stackr architecture. What you can build with it, to be honest, anything that can be built or converted into a state machine can be built as a micro-rollup, and this also composes with any smart contract on L1. So any state root that settles on an L1 can be composed with a micro-rollup, and that's what we like to say, that anything that can be built as a smart contract can be built faster, efficient, and better with a combination of a micro-rollup and a smart contract. So yeah, that's about it.
I want to know what response is given by the MRU to the user.
Oh, it could be anything. So let's say your MRU is running a application logic, which is payments, or like, I think that's like the easiest one to talk about, or it could be NFT, or it could be whatever. So the user submits an action which says that, okay, I want to transfer something. The MRU receives a transfer request, it processes it in its local state and gives the response back to the user that, okay, your response was processed. So A had 10 tokens, B had 15 tokens. A sent in a transaction request to the MRU that, hey, I want to transfer 5 tokens to B. and the response would be like, okay, yeah, that's done. So now on the MRU, the state moves from A equals 10 to A equals 5 and B equals 20. And this happens within milliseconds because it's like a centralized execution environment. Then this is something which we like to call as C1 confirmation, and we have multiple granularity in confirmation level. So on L1, it's like either you settle a transaction, the transaction succeeds or fails. But over here, we have 4 levels, actually 3 levels. Okay, so we have 3 levels of granularity on it, and that actually helps you to build different kind of UXs. So you can do a trade-off between confirmation time and security. So if you are settling faster, then you obviously you are losing a little bit on security. But if you are waiting for it, then you are actually getting the security as well as like the other benefits. So this is C1 when you immediately get a response. Then once the verification layer validates the block is correct, you get a C2 confirmation that okay, the committee said that is fine. This one is a centralized response. This one is a decentralized response. And then once finally things are settled, you get a C3 response that okay, finally my things are settled on L1 and it is immutable. We are also thinking of adding another layer of response, which is C4. That is the sovereign confirmation that even if a block is settled on an L1, the community through governance can come in and say that, okay, this block is something which we don't agree with, so we are going to revert it. So that is something which is in work. But yeah, that's like the overall structure of it.
So C4 is more for dispute resolution or?
Yeah, you can call it like fraud proof.
Okay.
Ideally, in the in most scenarios, you wouldn't need to run a fraud proof because there is a committee already checking it. So you get like soft commitment from here, soft commitment or soft finality from this layer. And then this soft finality is converted into a hard finality on L1.
Are you planning to have like this micro-rollups to communicate amongst each other?
Oh yes, I thought this was a little bit out of scope for this talk, but yes. So ideally, what would happen is these micro-rollups will talk through the Vulkan layer itself. So a micro-rollup will send in a block to this committee. The committee will give a soft finality, and then the other micro-rollup will be able to use that state through like a proof to progress something else. So the scenario would be like this: you have an NFT on MRU1, and your entire liquidity is on MRU2. So we like to call it liquidity hub, or you can consider it as a bank. So you don't need to own any tokens on MRU2. You just need to own an NFT, and through composability, what can happen is you want to buy an NFT on MRU2. You can just say that okay, the bank will pay you on MRU1, and you'll get an NFT on MRU2. So this is like a two-phase commit. But yeah, that's like how the messaging works in this context.
That's where the main economics gain come from.
Yeah.
Got it.
Yeah.
So these MRUs are something that that is inbuilt into Stackr, or anyone can plug in, play their own MRU logic. And that was the first part. And the second part is how will the user have to know which MRU he has to interact with, or is it like abstracted from?
Right. So Stackr is not a network. Stackr is an SDK. It gives you tools to build your own MRU. So this is not something that the Stackr network provides. Like the network is over here. You build it similar to any Web2 application. So let's say you want to interact with, let's say, CoinDCX or something. So CoinDCX will have its own application which has an MRU embedded inside of it, and the users will interact with it. So the discovery is to the user, but this works like a regular Web2 application. So if you want to interact on application A, you need to know application A's interface to get to it. So it's not abstracted. They can directly send a transaction to one MRU.
Can you post call data on L1 and get the transaction to execute on L1?
Yes, we have a module for base sequencing as well. So there is a contract that lives on L1. We call it bridge contract. And what can happen is you can send direct request to the bridge contract, and the MRU which is linked to this bridge will receive call data from that bridge, and you can have a logic to handle that bridge functionality and then take action based on that, and then like the same flow happens. This is like the most basic use case is token bridging.
Vulkan is what exactly? Like it's a set. You said it's a set of the committee. Who actually participates?
So Vulkan is a permissionless network wherein anyone who wants to secure Stacker network can stake and join this network and provide soft finality to the micro-rollup. So anyone can join this network. You just have to run a node and participate in the network, and then you receive requests from the MRU. You take part in a consensus and then produce blocks.
So is that L1 is equal to L2 validators?
Yes, you can say that. So it is not like the worst analogy, or like the best and the worst analogy would be of a shared sequencer, but it's not really a sequencer. Yeah, it kind of aggregates like blocks, something around that.
So what's the reward for the committee? What's the reward for the committee to participate actually, and how are you planning to bootstrap that initially?
Right. So right now the design is such that this is a proof of stake network, and to actually there would be rounds. So there would be 24 hours rounds, and whoever is participating in the network will get network rewards. So similar to how Ethereum works on the proof of stake network, wherein after every epoch you get new tokens minted. So this would be like an inflationary rewarding system, wherein if you are securing the network, you get token rewards for doing that basically. So it's a proof of stake consensus with inflationary rewards.
So is Vulkan standardized across what you call rollups, or is that also customizable depending on how the rollup is? Like depending on whether it's a game that's being built out or a people node.
So right now Vulkan is standardized across micro-rollups, but eventually what can happen is Vulkan can execute any kind of arbitrary WASM logic. So we are thinking of a situation wherein Optimism or Arbitrum can actually send their transactions to this Vulkan layer, and it kind of becomes like a proof aggregator for all the rollups. However, this is something which is in future. We want to make sure that Vulkan operates well with all the MRUs for whatever use case. It could be intense, it could be deepin, it could be whatever. But this network acts as a checkpoint for any block that is going from Stackr to L1. So this is like that kind of situation.
How do users engage with, like for example, they have all these app-specific rollups that's built. Okay, how do users engage and check out what's going on underneath the hood? Do you like build out two rollups, and do they have to build out their own explorers, or are you providing an interface for that?
Yes. So for MRUs, every MRU has like I'll show you. So we have a state explorer for all the MRUs. So you can see whatever state the MRU is operating on. We will have a separate Vulkan explorer, which will give you visibility on what the Vulkan network is doing. So once it receives a block, once it verifies the block, once the block is settled on L1, you will get all the things from the Vulkan layer, and then finally you already have like explorers for DA and L1 available. So it is up to the MRU. Like MRU gets an API that okay, this is my state, these are the transaction, all of those things. It's up to the MRU to build their own like interface on top of it. So we have an API, you build your interface.
Understood. And also for the DA, you mentioned that the app has the choice of picking up a DA.
Yeah.
How does that get reflected, like from a user perspective? I mean, like as an app, do you have the ability to toggle it, or is it one DA that's getting continued? And what's the story there?
Right. So actually, we built a middleware between the Stacker layer and the base DA. We call it GoDash, and there is an interface for it which is called Blob Daddy. So the purpose of that is that aggregator will be working on top of DAs, and it will be balancing the data across different DAs. So in the future, we expect more DAs to pop up. We already have 5 of them: Avail, Celestia, Ethereum, Eigen, Espresso, a couple of more near. I don't know. It'll also keep growing. So we need a service that can sit on top of all the DAs, which can perform those kind of things. So from the user, they don't care about, they shouldn't care about it. So they would be completely abstracted away. For them, it would just be like interacting with the Web2 application, and that is the biggest Web3 UX problem that we have. That you need to have a wallet, you need to do some. You need to get tokens to interact with it on all of those things. For us, MRUs just need to sign a message and that's all. You don't even need to have any tokens. All of the L1 logic and all the chain logic is handled between the Vulkan and the settlement layer. So everything else is just abstracted away. So the users, in the ideal world, if you have an embedded wallet, the users might not even know that they are interacting with a blockchain application. And that is the future that we want to build.
But again, it's kind of created this, verify, don't trust policy scenario where we want to like check into what's going on with the block explorer.
Yeah. So if you are, you always have visibility on whatever is going on between the MRU and the Vulkan layer, and always have visibility between what's going on between Vulkan and DL. So you can pick anything anytime. You can even create a fork of anyone's MRU and run a light client for that MRU and see if the MRU is doing the right job or not. Or you can just join the Vulkan network to do that and get rewarded.
That's interesting. This stuff is going very bonkers. What I mean, is it possible to kind of create an EBS instead of bootstrapping your own network with?
Yeah, that's what we are thinking about. Okay, we are way out of the scope of the talk, but yes. So the proof of stake consensus is supposed to be like a dual staking. I can talk about it afterwards as well. So it's supposed to be like a dual staking model eventually, but we are still not sure about EigenLayer's dual staking model yet, because then your token loses value in front of ETH. So that is something. There are like pros and cons to building an EVS. So yeah, we just verify, but we're just thinking about those things right now.
So, I mean, you must have spoken to a lot of dApps right now, and they would have their own requirements about how the finality would be in terms of how the verification would happen. Do you find that to be in conflict with the standard of Vulkan, or how are you guys working with that?
Oh, so the best part is WASM. So you build anything anyhow, and you just give us a WASM file that can execute your logic, and we just work with it. Yeah. All right. So I'll just take like 2 more minutes to show an example app that we built using this SDK, and that is something which others can use as well. So right now in the current space, we have a lot of like the current narrative is some. Are we going to take off in a minute? Yeah, to the. So we built an application which is called Pointy, and we know that in the current DeFi space, points are something which is very which is a very big narrative right now. And the purpose of that is all the point systems, most of the point system that we have are opaque and not like you don't have any visibility into how those points are given out, and then suddenly the protocol decides to change the way how the point systems work. So we built a micro-rollup that can handle points and points only. So it cannot do anything else except doing points, but it does it very efficiently. So what you can do is you can just create a point system, and that can settle like 5,000 transactions in $5, which is I don't know whatever that comes out to be, and all of the points are verifiable on chain. So let me just please show you. By the way, this is live. If you guys want to check it out or want to integrate into your system, you can do that. So you just log into it, and we don't need any wallet. So if you check this out, like this browser window, it literally says no crypto. So it does not have any wallet. So you don't need wallet to interact with it. We embedded a wallet inside the application, and this is how the point system looks like. So we have a leaderboard. So all these people were granted points from our side. So we just, yeah, of course, I'm at the top of the leaderboard. But all the events that were done gets logged, and all of these things are on chain. And to do that on smart contracts, you would actually be spending like a lot of money to get all the things in. But the benefit of a micro-rollup is that you can do it like in just like a couple of cents, like less than I think it's 100th of a cent, and all of the details are settled on a block on a DL layer, and you can come in and verify it on your own. So if I go on to this one, I hope it shows up properly. Yeah. So if you check out this transaction, you can actually find like this is my roll-up data, and this transaction is over here. You can find it inside payload. So this was my address. This was the event, which is login, and this was the timestamp when the event happened, and it granted me points. So I can actually go ahead and use this point system, and we have an app for that as well, somewhere over here. So since all the points are on chain, you can submit a. I hope this is visible enough. So if you have all the points on chain, what you can do is you can do an immediate or a subsequent running airdrop. And right now, this is the point scheme contract. I can just verify my proof. This is the proof data which is on rollup, and that's just all you want. You don't need the entire EVM proof, and I can just verify my proof that yes, I have one second. Yes, that this is actually valid, that I do have 2800 points on chain. And if I want to claim certain points, I already claimed 1900. And you can see that I can even immediately convert those points into tokens. So I have 1900 tokens right now. I can go ahead and claim, like, let's say 300 more. And if I click on claim and I confirm it, will take a couple of seconds to get passed, and the state roots from the L1 is getting verified. I have my token claim. Okay, it's claimed now, so I have 2200 points claimed. And if I go back onto token, I can see that I was able to redeem my points against ERC20. So this is like a direct airdrop use case. You can actually extend this points claim contract to do anything on your own. And it can be tokens, it could be some other incentivization. You can plug into someone else's point system and vampire attack them. You can do whatever you want. So yeah, that was like a basic demo of what you can build with micro-rollups. Thank you. That was all.